Hello everyone. I hope I am audible and my screen is visible clearly. And so this is tutorial uh, 6. Okay. So no, sorry. This is tutorial 5. I think last day it was tutorial 4. Tutorial tutorial 4. So this is tutorial 5. So I hope I am audible. So let's start the tutorial 5. Tutorial 5 of the course measure and integration. I hope the code is NOC NA. So this is the thing. So first in this class, what we will do, we will first solve a problem which is pending from the last, which was pending from the last class, and after that we will go to today's content. So let's start with the that problem. So I think this was the problem. So there was the problem. Let me first find that problem. So here is the problem. The problem is that let xx be a measurable space mu with a measure mu, and fn be a sequence of measurable functions defined on x converging to f almost everywhere. It is necessary. Is it necessary that f is measurable? The answer is no. But I'm in last day. I am not able to give counter example. So pending problem. So let x s mu be measure space. So that means x is a set, non-empty set, and s is a sigma algebra on x, and mu is a measure on that sigma algebra. And let fn be a sequence be a sequence of measurable functions measurable functions be a sequence of real valued measurable functions, because that is needed. Be a sequence of extended real valued measurable functions, extended real valued measurable measurable functions. So that means f is a real value, but it can take value infinity as well. So that is why it is extended real valued measurable functions on x, which converges almost everywhere to a function f. Then question is it necessary that is it necessary that f is also measurable? And in the last day I have said that the answer is in general no. But when this is true, I'll give a counter example where there will exist a sequence of measurable functions which converges to a functions f almost everywhere. Okay, but which converges to a function almost everywhere, but the function where it is converging f is not measurable. That I have to prove. Okay, and when this is true, that means if a sequence of real valued measurable function is there and that convergence almost everywhere to a function f on x, so when that f is necessarily measurable, that is the answer is the complete space. If the measure x s mu is the complete space, then the answer is true. Okay. So now let's first give a answer in general is not true. Answer in general is not true. So the question is why the answer is in general not true. So as I have said that the answer is in true when the measure space is a complete measure space. So if I want to get a counter example, so we have to look at the measure space which is not complete. So let's first concentrate on a measure space which is not complete. Let's take x is equals to real number and mu be a mu be the usual Lebesgue measure. Mu be the usual Lebesgue measure. Lebesgue measure on the Lebesgue measurable sets. Lebesgue measurable sets S. Okay, SR that I am writing. This is the Lebesgue measurable sets. Now, so that means now let's consider let BR be the collection of all Borel measurable sets. Now it is known that Borel measurable sets are actually subset of this. In fact, this inclusion is proper. Here is the point. In fact, this inclusion is proper. Okay. So that means there must exist a Lebesgue measurable set which is not Borel measurable, and you can, I mean that this is obviously existential. It is known. So existential it is known that there exists a Lebesgue measurable set which is not Borel measurable. In fact, this inclusion is improper. So that means this will be subset but not equal. Okay, this is the first thing. So now we have taken that mu is the usual Borel measure, right? So now let's take R, that is the set, and the Borel measurable set, and the measure mu restricted on the Borel measurable set, because mu is defined in general on SR. This is Lebesgue measure SR. So here I am taking this one. Okay, this is the space. Consider so consider the measure space is this. Okay, this is the measure space. Okay, it is not, let A be an element in SR, but A does not belongs to BR, and this is possible because the inclusion is proper. Okay, then, and also one can, without loss of generality, also such that A is subset of C, where C is Cantor set. Okay, that we can consider, we can take actually. This is the existential we can do. Okay, so that is little explanatory is needed. Explanatory is needed for this. I am trying to avoiding that one. So we are taking a set which is Lebesgue measurable and but not Borel measurable, and the set is subset of C, where C is Cantor set, and then the measure of the set C is actually 0. Okay, this is known. But let's consider the f is equals to the characteristics function A, that is f of x is equals to 1 if x is coming from A, and 0 if x does not coming from A. And consider the sequence fn from x to r extended real value, that you can write it as 0 to infinity, by given by fn of x is equals to 0 for all x belongs to real number. Okay, so that means then as measure of the set C is equals to 0, then clearly Fn converges to F on C complement of C. So then Fn is converges almost everywhere to F. Okay, but note that Fn is Fn each Fn. Note that for each n belongs to natural number n, Fn is Borel measurable. Lebesgue measurable means inverse image of every set of the form this has to be inverse image of a function is Lebesgue measurable if inverse image of this set is contained in the Lebesgue measurable set, and Borel measurable if this is equals to this is the thing. So now as it is constant and 0, that means if a set contains 0, then inverse image will be the full, that is R. If a set does not contain 0, then inverse image will be empty set. So that's why as empty set and 0 at full set R is always in Borel measurable sets, or it is real. So these FNs are actually both Lebesgue measurable and as well as Borel measurable. Okay, so then Fn is a sequence of Borel measurable functions which converges almost everywhere to a function f. But my claim is that f is not Borel measurable. As f inverse of half to infinity is equals to a, because it is given that f of x is equals to 1 if x is inside a and 0 if x is not inside a. So that means the interval which contains 1, the inverse image of that interval will be the full set A, and if a interval does not contains the point 1, so that means the if a interval does not contain 1, I mean, so that can either, if the interval contains 0 and both 0 and 1 both, then the inverse image will be full R. If the interval contains only 0, then interval will be inverse image will be A complement. If it contains only 1, then inverse image will be A, and if does not contain 0 and 1, then it will be just only empty set. So in that case, the inverse images are like A complementary and real, and all of them are there. So therefore, but the fact is that this is does not belongs to the Borel measurable set, because this is how we have started the things. So that's why that so therefore the almost everywhere limit of a sequence of measurable function need not be measurable functions need not be measurable. So that's why this justifies the answer. But the one more note I can add here is that note that first note f is Lebesgue measurable. we have constructed a measure in such a, we have constructed a function in such a way that the function is not Borel measurable. But why the function is not Borel measurable? Because inverse image of this ray half to half to infinity is actually A, which is not in the Borel set. But thus this set is actually but this set actually is okay. But this set actually is sorry. This set actually F is Lebesgue measurable and okay. But this set is actually inside the this set A is inside this A is inside the what is called the Lebesgue measurable sets. Okay, so why A is Lebesgue measurable set? Because A I have taken subset of C, and the measure of the set C is equals to 0, and the measure is Lebesgue measure. So Lebesgue measure is complete. So as the Lebesgue measure is complete, so therefore any set which is subset of a set of measure 0, so that set has to be inside. So if so in that case, as A is subset of C and measure of C is equals to 0 and mu is complete, so therefore A has to be inside the measurable sets. Okay, so this is the thing. So I can remove this. First thing is that, and second note is that almost everywhere limit almost everywhere limit of a sequence of measurable functions is again measurable again measurable if the measure space is complete. Okay, so this is the thing. If the measure space is complete, then we are done. So in particular, if we consider the Lebesgue measurable space, Lebesgue measurable functions, then almost every limit of a sequence of measurable functions is again measurable. Okay, so because Lebesgue measure is on the Euclidean space basically is actually um, complete measure. Okay, so now before going to the next problem, I will first uh, recall some recall some definitions basically. So so recall first definition. You know Egorov's theorem is there, and motivated by Egorov's theorem there is a definition of almost uniformly almost converges in almost uniform. Almost uniformly convergence. Let X S mu be a measure space and Fn be a sequence of real valued measurable functions on X, real valued measurable functions on S on X, basically real valued measurable functions on X, and then we say we say Fn we say that the sequence converges almost uniformly to a measurable functions to a real valued measurable functions f condition if for every epsilon greater than 0, if for every epsilon greater than 0 there is a measurable set f, there is a measurable set f measurable set f subset of x such that measure of the set f is less than epsilon, and fn converges to f uniformly on f complement. Okay, this is what is called the, so that means almost uniformly convergence means that their f sequence is said to be almost uniformly convergence if for every epsilon greater than 0 there exists a measurable set f subset of x with the measure of f is less than epsilon, and fn converges to f uniformly on the f complement. Okay, and it is called almost uniformly Cauchy. Uniformly Cauchy if for every epsilon greater than 0 if for every epsilon if Fn is uniformly Cauchy and is uniformly Cauchy on F complement with the same definition. I mean the same definition. It is uniformly Cauchy on F complement means that for, that means that that for every delta greater than 0, that means if for every delta greater than 0 there exists a natural number n that may depend on epsilon, that doesn't matter, but natural number n such that for all m and n greater than equals to n, that mod of fm x minus fnx, this one is less than delta for all x belongs to f complement. This should holds. Okay, so this is what means the uniformly Cauchy. So okay, so now there is a theorem. I will just say that uniformly Cauchy if and only uniformly a sequence is uniformly converges if and only if it is uniformly Cauchy. Okay. Now the second definition, convergence in measure. So this almost uniformly sometimes denoted by AU, almost uniformly, or almost Cauchy, that almost uniformly Cauchy, that I think I will always try to be right every fully. So this is sometimes denoted by almost uniformly, that AU, A dot U dot. Now in another definition, convergence in measure. So what is the convergence in measure? That a sequence let with the same reference with the same definition with the same notations in the above definition with the same notations in the above definition, the sequence fn is said to be converges in measure to f converges in measure to f if for every epsilon greater than 0 the this set has limit 0. For every n, we can define this set, that collection of all x belongs to capital X, um, such that mod of fn x minus fx greater than equals to epsilon. This has to be limit, has to be 0, and almost and denoted by fn converges to f in measure, the corresponding measure, and all converges Cauchy in measure, Cauchy in measure if for any epsilon greater than 0 and delta greater than 0, this set has to be Cauchy sequence. A Cauchy sequence, yeah. This set has to be Cauchy sequence. Main point is that converges in measure means for every epsilon greater than 0, this sequence of set, sorry, this sequence of real numbers, because this is right now real number, because I mean the thing is that we are considering x belongs to x such that mod of f or fnx minus fx greater than epsilon. So this is right now a set, suppose en. Okay, so now the Cauchy a sequence is for a sequence is I mean one can say that this is just, we can denote that en epsilon. Okay, en epsilon. So now the sequence is said to be converges in measure means for every epsilon greater than 0, limit n tends to infinity, en mu en epsilon, that has to be 0, and Cauchy means the sequence for every epsilon greater than 0, the sequence, this is Cauchy sequence. So that means for every delta greater than 0, we should have en, I mean then we can, that we can equivalently prove actually, that I'm writing that way. So that means this is means that for every epsilon delta greater than 0, there exists a natural number n. There exists natural number n such that for all n and m greater than equals to n, the measure of the set x belongs to capital X mod such that fnx minus fnx, this is greater than equals to epsilon. This set has measure is greater than less than delta. So this is what we mean by Cauchy measure. Okay. Now also similarly, a sequence is Cauchy measure if and only convergence is measure, and we know what is the almost everywhere convergence. So now let's go to the some problems. Okay, first problem. Let x s mu be a measure space. Let fn n equals to 1 to infinity and gn be two sequence of real number, sequence of real numbers, be two sequence of real valued measurable functions, actually be two sequence of real valued measurable functions, real valued measurable functions defined on x such that gn equals to fn equals to gn almost everywhere for every n. Okay, now question is that if fn converges to f in measure, this is symbols measure, so that gn converges to f in this same measure where f is a real valued measurable functions defined on x. Real valued defined on x. Okay, so now let's try to do this problem. So what this problem says, x has a measurable space and we have two sequence of measurable functions fn and gn, and such that each functions fn are almost everywhere equal to gn, okay, for every n, and it is given that fn converges to f, and we have to show that gn converges to f in measure, that we have to show. That means what we have to, by definition we have to show that by definition we need to show that for any epsilon greater than 0, limit n tends to infinity, collection measure of the set all x belongs to x such that mod of g nx minus fx, this is greater than equals to epsilon, this set has to be 0. This is what we have to prove. Okay, now first note that as for each n belongs to natural number, gn is equals to fn almost everywhere on x, there exists a set fn which is subset of x such that measure of this set fn has to be 0, and gn x is equals to f of nx for all x belongs to fn complement. Okay, this is the thing. So that is what is mean by convergence is almost everywhere equal. Okay, now also it is known that fn converges to f in measure. So now for this convergence we have, so that means what we know, that is for any delta greater than 0, the limit of this set n tends to infinity, x belongs to x such that mod of f of nx minus f of x greater than equals to f delta, this is equals to 0. Now note that g of nx minus f of x, this is can be written as g of nx minus fnx, I am writing is directly, this less than equals to mod of this one. Okay, so now I want to prove this one basically, right? So now first of all, whenever so this will give that the set x belongs to x such that mod of gnx minus, or this gives that one can write, this gives that mod of gnx minus, sorry, the set x belongs to a such that mod of gnx minus fx greater than is equals to epsilon, that is subset of all x belongs to x such that mod of gnx minus fn x greater than or equals to epsilon by 2 union all x belongs to x union, this is subset, such that mod of fn x minus fx greater than or equals to epsilon by 2. Okay, note that if an element x is in here, that x belongs to uh, this set, x belongs to the other mod of gnx fn x is less greater than or equals to epsilon, so that means this has to be greater than or equals to epsilon. Okay, now as this is greater than or equals to epsilon, so that gives gnx plus fnx just a minute. Hmm. Then x has to be here. First of all, x has to be here. Why x has to be here? Because if x is not here, so that means we have that either that means for if x is not here, I mean the x for which this is happened, that mod of gnx minus fx greater than or equals to epsilon. So now my claim is that x is here. If x is not here, then what we can say? Suppose x is not here. That means as x is not here, that means for both the case we should have this one epsilon by 2 and fn x minus f of x, this is also less than epsilon by 2. This both has to happen. But if these two happen, then one can say that mod of gnx minus fx, this is strictly less than epsilon. But this is contradiction, because we are taking that mod of gnx minus fx greater than or equals to epsilon. So this can't be strictly less than epsilon, because if x is, my point is that if x is not this union, then for that particular x we should have these two particular things. For these two we should have particular these two things, these two simultaneously, this should happen. If simultaneously this should happen, then mod of gnx minus fnx, that has to be less than or equals to this thing. So that is a contradiction. So therefore this has to be, this is the truth, this gives that, this two gives. Okay, so now then what we can say is that the measure of this set, then measure of this set x belongs to capital X such that mod of gnx minus fx is greater than equals to epsilon. This one has to be less than equals to, I'm writing the decision below because it is main note, or I can write never. Then measure of the set x belongs to x such that gnx minus fx mod greater than epsilon, this one is less than equals to measure of the set x belongs to x such that gnx minus fnx is epsilon greater than epsilon by 2 plus measure of the set x belongs to x such that mod greater than equals to epsilon by 2. Okay. So now note that this set, particularly this set, the set x belongs to capital X such that f gnx minus fnx greater than equals to set, this set is actually subset of the set fn. This set is subset of the set fn, but the measure of this set is actually 0. So therefore, what I can write is that this one is equals to measure of the set x belongs to x such that f of x minus f of x, this greater than equals to epsilon by 2. So this set, this is the thing. But as for every, so here I can choose, that is, I can choose here delta as epsilon by 2. Okay, so but limit n tends to infinity, mu of x belongs to x such that mod of f of nx, f of x mod greater than equals to epsilon by 2. This has to be 0 for all epsilon greater than 0, and this gives that limit n tends to infinity mu, I mean measure of the set x belongs to capital X such that mod of gnx minus f of x, this greater than equals to epsilon, this has to be 0. Okay, for all epsilon greater than 0. So this gives that gn converges to f in measure. So this completes the proof. Okay. So I'll go to the next problem, but just few seconds only. Okay. So let's go to the next problem. So what it says, let X S mu be a measure space. Let X S mu be a measure space. Measure space. Let Fn be a sequence. Be a sequence of real valued measurable functions defined on X converging in measure to a real valued measurable functions f defined on x. So this is the information it is giving, that fn converges in measure to f. If the sequence fn, that means same sequence fn, is almost uniformly Cauchy, uniformly Cauchy, so that it converges to f almost uniformly. So first of all, if a sequence is almost uniformly Cauchy, that must have converges to some point, but it is already converges in measure, so that means there has to be converging to the point. Okay, so it can be done in short. That short is that there is a theorem. So let me go to that theorem. I'll prove the full one, but there is a theorem. That theorem says short proof. First of all, let's give the short proof. That short proof says that if the sequence fn converges in measure, if a sequence fn converges to f in measure, then there exists a subsequence. There exists a subsequence f nk which converges to f almost everywhere. So now first it is saying that if a sequence fn is converging in measure to the function f, then there exists a subsequence fnk which converges to f almost everywhere. Now as fnk converges to f almost everywhere, so then, and also it is giving that fn is almost uniformly Cauchy. So combining this to the fact that fn are uniformly Cauchy, we get that f is the almost uniform limit. Combining this with, okay, let me give the short proof as well. Combining this with almost uniform, this with almost uniformly Cauchy, one can get almost uniform convergence, almost uniform convergence. Uniform convergence. So let's okay, just a minute. So this is not short proof. Actually, I have to prove this one only. Okay, so this is another way proof. I am giving another way, another alternative argument. Alternative argument. But for these two, I will first give two theorem statement. I am just statements that statements is are about almost uniformly. Then statement is that Fn is almost uniformly Cauchy. That gives there exists a function g measurable that I have already said that almost uniformly Cauchy means it is there exists a subsequence which there exists a almost uniformly Cauchy means there exists a function where it will converge in almost uniformly. Okay, and similarly, and if it is converging almost uniformly, that has to be almost uniformly Cauchy. There is no doubt. Similarly, if a sequence converges in measure, then that will be Cauchy in measure, and if a sequence is Cauchy in measure, then that will be converges in measure. Okay, that if and only if condition is there. So let Fn is a sequence almost uniformly Cauchy, then there exists a g measurable function basically. There is a measurable function g on x such that Fn converges to f almost uniformly. Okay, this is the first part. This is the first part, and vice versa is automatically there. Okay, but second statement is that these are the theorem I am writing is as the statements because I am not writing the full details. That is like XS mu with the measure space and Fn is a sequence of real valued measurable functions. Then Fn is almost uniformly Cauchy. Then there exists a sequence. There is a function where it will converge almost uniformly. And the second theorem is that if Fn converges to G in almost uniformly, then that implies that Fn converges to G in measure. Okay. So what we have to prove? We have to prove that for every epsilon greater than 0. Now we need to prove that also it is given that there exists a subsequence such that Fnk converges to F almost uniformly. Sorry, it is given that okay, Fn here Fn is sequence of real valued measurable functions defined as converging in measure to a real valued measurable function f defined on x. But also it is given that Fn converges to f in measure. Okay, Fn converges to F in major. Then by problem we have solved in the last class, one can say that F and G are almost everywhere, equal almost everywhere. That we have proved in the last class. That if we go back to the last class, last problem, so what it is says that if Fn is a sequence of real valued measurable functions defined on X converging to a measurable real valued functions F defined on X, if G be a real valued measurable function defined on X such that F equals to G almost everywhere. Oh, this is in other way. So you have to prove that then F equals to G almost everywhere. That we can do also. Given that is a then first claim, then claim one is that F equals to G almost everywhere. That is also one can do that we have to show that that means the set X belongs to capital X such that mod of Fx minus Gx is greater than epsilon for every epsilon greater than 0 is equals to 0, right? But for every epsilon greater than 0, for every epsilon greater than 0. Now for every epsilon greater than 0, the set X belongs to X such that f of X minus g of X is greater than equals to epsilon, okay, is greater than equals to epsilon. This one is subset of the set X belongs to capital X such that so this can be written as the subset of the set X belongs to capital X such that mod of f of X minus f of nx mod is greater than is equals to epsilon by 2 union all those X belongs to capital X such that mod of gx minus mod of f of nx, but mod of gx minus mod of minus fnx, this is greater than equals to epsilon by 2. So like the previous argument, one can show this one, and as fn is converges to f in major and fn is converges to g in major, so therefore these two set has major is will go to 0. Basically the thing is that limit n tends to infinity. Now what we are getting that x belongs to capital X such that mod of f of x minus g of x this greater than or equals to epsilon. This one is less than is equals to measure of these two set and whose limit is going to be 0, okay, and this is for all n. Okay, so one can write this one is less than is equals to limit n tends to infinity all x belongs to capital X such that mod of f of x minus f of nx this greater than or equals to epsilon by 2, this one plus limit n tends to infinity x belongs to x mod of gx minus mod of f of x which is greater than epsilon by these two, okay. And why these two? First of all, because for every n, I mean the point is that we can, okay, so I have written little wrong, I have written limit n tends to infinity mu of this, and similarly limit n tends to infinity mu of this, okay, these two. So first of all, what we are getting that for every epsilon greater than 0, this particular measure thing is actually less than equals to these two things, measure of this and measure of this, but this is true for every n. So therefore as this is true for every n, so we can write this one, but these two are the 0 for every epsilon greater than 0, because fx is converges to f in major and fnx is converges to g in major, so that's why these two has to be 0. So therefore from this one can say that f is equals to g almost everywhere. So this settles the first claim, that claim is that f equals to g almost everywhere. Now what I have to prove is that if f equals to g almost everywhere and fn converges to g in major, what I have to prove actually that fn converges to f such that I have to prove that. Now I have to prove that Fn converges to F almost uniformly, right? This is my main target. So now to prove Fn converges to F almost uniformly, what we have to do that? We have to do that for every epsilon greater than 0, you have to find a set of major 0 outside which the every epsilon greater than 0, there we have to find a set of major less than epsilons. Outside of that set, the measure has to be, I mean, the outside of that set, the function has to be converges to. So, but we know that, and we know that Fn converges to G, we know that, we know that Fn converges to F almost, sorry, Fn converges to G almost uniformly, and F equals to G almost everywhere. So these two we know. We have to use these two facts and prove that. Okay. So now for every epsilon greater than 0, now note that mod of f of nx minus fx, this one can be written as mod of f of nx, this less than equals to mod of gx plus mod of gx minus fx. So therefore, the set x belongs to capital X such that mod of f of nx minus f of x, this one is greater than epsilon for any epsilon greater than 0. Greater than 0. This gives that this one greater than equals to 0 subset of measure of this set, or right now I'm not writing measure, subset of x belongs to x such that mod of f of nx minus g of x, this one is greater than or equals to epsilon by 2 union all x belongs to capital X such that mod of gx minus fx is greater than or equals to epsilon by 2, this two. Okay, but the measure of, we know this one, but the measure of the set x belongs to x such that mod of f of nx minus this one is greater than or equals to epsilon by 2, this one is less than or equals to measure of the set x belongs to capital X such that mod of fnx minus gx greater than or equals to epsilon by 2, this measure plus measure of the set x belongs to capital X such that gx minus fx greater than or equals to epsilon by 2. But as we have got that for every epsilon, the f and g are almost everywhere equal, that means the measure of this set is actually 0. For every epsilon greater than 0, this set is 0. So that means this one can write okay, this one can write this here, and this one, as n tends to infinity, this one has to go to 0 for every epsilon greater than 0. Therefore, also as fn converges to g in g almost everywhere, now I can use both of them, almost everywhere and almost uniformly. Then fn converges to f almost everywhere, because you know that if this is 0, then this has to go to 0. If this is going to 0, that means that for every, I mean, the set where So basically, as fn goes to 0, fn almost everywhere, then uh, for epsilon greater than 0, there exists the measure of the set, this set basically, x belongs to x, such that fn x minus gx, this one is greater than epsilon by 2. This set has to be less than, measure of this set has to be less than epsilon by 2. As the measure of this set is less than epsilon by 2, then measure of the set x belongs to capital X, such that mod of fn x minus fx is greater than equals to epsilon by 2. This is less than epsilon or epsilon by 2, whatever is preferred for whatever is required. Okay, so that means, that is, there exists a set f So this is very trivial. Basically, thing is that this set is subset of, this set is subset of some f, okay, because that has to be, I mean, outside of that set fn has to be converges to g, and similarly outside of that set, so this directly will give, actually this is not much. Okay, let me just, still if I can give any statement about that, so let me just first find. This will give, actually such that measure of f is less than epsilon by 2, and x belongs to x, and fn converges to g, g for all, or one can write uniformly on f complement, right? So that is for given delta greater than 0, there exists a natural number n naught belongs to natural number n, such that mod of f of nx minus gn nx is less than delta for all x belongs to f complement. This is what we have to, and for all n greater than or equals to n naught. Now we can take everything as it is. Now so that is, one can say that is for epsilon there exists an n naught such that fnx is greater less than epsilon by 2. But so that gives mod of f of nx minus fx, this is less than epsilon by 2 for all x belongs to f complementary. Okay, this will hold less than epsilon for all x belongs to f complementary. No, I think I'm making, yeah. So that means for every delta greater than 0 that I can write less than delta such that is there exists this for all x belongs to 1. Yeah, so that means if fnx minus fx will has to be less than epsilon for all x belongs to fc and for all n belongs to natural number. If this does not hold, first of all, if this does not hold, that means that means um, that will contradict this one. If that does not hold, that will contradict to this one. Okay, because suppose the set x such that mod of fnx minus fx not less than epsilon, that means that greater than epsilon collection of for all x. Okay, that set has to be contained in here the collection of basically suppose for a fixed n, suppose for a fixed n greater than n naught, for a fixed n greater than n naught, the collection of x belongs to x such that mod of f of nx minus f of x, this um, less than this greater than equals to epsilon, this has to be measure of this set has to be, this has to be subset of measure of this set has to be less than equals to measure of the x belongs to capital X such that fnx minus gx greater than is equals to epsilon by 2, but this measure is less than epsilon by 2. So therefore the collection of points where this will hold, the measure of that set will automatically be less than epsilon. This is what my point. For any n greater than n naught, the collection of points x belongs to capital X such that mod of fnx minus fx greater than equals to epsilon, so that set has to be measured less than epsilon by 2, and in particular epsilon. This completes the proof. Okay, so now let's go to the another problem. What it says, similarly let x s mu be a measure space, let fn be a sequence of real valued measurable functions defined on x, converging in measure to a real valued converging measure to a real valued measurable function f defined on X if the sequence fn is pointwise Cauchy, almost everywhere, so that fn converges to f almost everywhere. So what it is given first? It is given that convergence is major. Okay, it is given that convergence is major. Okay, it is given that the sequence fn converges in major, first of all, to f. Secondly, is that fn is pointwise Cauchy, so that fn equals to f almost everywhere. Fn converges to f almost everywhere. Okay, so now as fn is pointwise Cauchy, almost everywhere, then the set such that fn is not Cauchy measure of f will be 0. The set of points where the fnx is not Cauchy is measure of 0. Now, for all point x seen in f complementary, f of nx converges to some point y, which we denote by g of x. Okay, so now define g from x to y. So define g from x to the real valued function by g of x is equals to limit n tends to infinity f of nx for all x belongs to f complementary and is 0 if x belongs to f. So therefore, fn is converging to f, then fn converging to g almost everywhere on x. There is no doubt about this because we have constructed the function g in such a way. Okay. Now claim is that what you have to prove that fn converges to claim is that f equals to g almost everywhere. I think this is what, right? Claim is that fn converges to f almost everywhere. That is f equals to g almost everywhere. This is what you have to prove. Okay. So that means what you have to prove that Okay. It is given that the convergence in measure, that is also there. I don't want to any. Um, we have used a theorem that if a sequence is convergence is measure, then there exists a subsequence where we have used that theorem. Okay, let me state the theorem again. Okay, so the theorem, this is the theorem. I just want to, I think I have already mentioned place somewhere. If x with the above notation, with the same notation as the problem, with the same notation as in the problem statement with the same notations as in the problem statement, if fn converges to f in measure, then there is a subsequence, there is subsequent fnk converges to f almost everywhere. Okay, so that means the point x belongs to capital X such that, that is the point f belongs to capital X such that f n k x does not converge to f of x, that is if I write f g, then that is if this, then measure of the set g is equals to 0. Okay, as k tends to infinity. Here is the k tends to infinity. This is the thing. Measure of this set is 0. Okay. So now with this theorem, we have seen the set f. Outside of that set, fn is converges to somewhere, and outside of this set, or sorry, outside of the set f, uh, fnx converges to g. Okay, and outside of the set g, sorry, fnx converges to this function g, and outside of the set g, this fnk converges to the function f basically. Okay, and so that means if the point is in outside of the set f, then f nkx converges to fx, and if nkx converges to gx, that implies f equals to g on f intersection g complement. But okay, f union g complement. Outside of a set, some condition holds. Outside of a set, basically we need to that. Here you can write the f complement intersection g complement. Whenever x is there, we have to this. That is when H is equals to F union G, then for all x belongs to or all x belongs to F union G whole complement f of nkx or f of nx, f of nx converges to g of x, which is equals to f of, basically I have to write f of x, which is equals to g of x. Okay, and also measure of the set f union g is less than is equals to measure of the set f plus measure of the set g, but both measure of the set f and measure of the set g, that is 0. So therefore this is happening due to subadditivity, so therefore this is equals to 0. That means fn converges to f almost everywhere. This completes the proof. Now let's do another problem. That 4.5, problem number 5, what it says, let x s mu be a measure space. Measure space. Let fn be a sequence of be a sequence of real valued measurable functions defined on x such that every subsequence has a further subsequence, such that every subsequence has a further subsequence which converges in measure to a fixed real valued measurable function. This is the important thing, fixed real valued measurable function defined on x, so that fn converges to f in measure. We can write it here. We can write it here in measure. So what it is asking, let xs is mu be the measure space and fn be a fn be a sequence of real measurable function with the property that every subsequence has a further subsequence which converges in measure to a fixed real value. Here it is the one fixed one is the very important thing. Subsequence f defined on x so that fn converges to f in measure. Okay, let me give some time here. Okay. So here is the interesting fact. Here we are given that every sequence, this is the statement, and this statement is true for a general sequence as well. Real number and convergence that sense also. Every sequence has a further subsequence. Every subsequence has a further subsequence which converges to a fixed limit. To a converges in measure to a fixed limit. Fixed limit function or fixed real value function. Okay. Okay, now the claim is that if Fn is not converges to F, if Fn is not converges to F in measure, then by definition there exists an epsilon greater than 0. There exists epsilon greater than 0 such that limit of this measure actually that x belongs to x such that this is greater than epsilon equals to 0, this limit is not equals to 0. In general, it has to be 0 by definition. That means we have found an epsilon naught for which we are able to found an epsilon naught such that limit enters to infinity, mu of this is not equals to 0. Now, as the measure of this is not equals to 0, measure of this particular thing, sorry, limit of this particular real number is not equals to 0, that means for every epsilon greater than 0, for every, so now consider it is, let we can for simplicity we can consider en is equals to all those x belongs to capital X such that mod of f of nx minus mod of fx less than or equals to epsilon naught. Okay, this is the thing, we can write it as en. Okay, so my point is that if as then with this identification limit n tends to infinity, mu of en that is equals to 0. This is what we have, right? So now as mu of en is not equals to 0, that means for any delta is equals to 1 by n, okay, for k I can take, for any k belongs to, for any k belongs to natural number n and delta equals to 1 by k, there must exist a subsequent nk, as this is not equals to 0, not converging to 0, that means whatever nk I can choose, whatever delta I can choose, if this is 0, then what I can do that for every delta greater than 0, there exists a natural number m naught such that whenever n is greater than or equals to m naught, mu of en minus mod of mu n, this is less than delta. This should happen. But here for what we are getting, for every delta greater than 0, this should happen. Okay. Right now, there exists a delta greater than 0. Okay, so let me go through the definition. If the limit was 0, then what we have to done, that there exists for every delta greater than 0, there exists a natural number n such that for every n greater than n naught, mod of mu of en has to be less than equals to less than epsilon. So keeping in mind this fact, so this definition, what will be that there exists delta greater than 0. So let me write there exists delta greater than 0 such that for all n belongs to natural number, there exists and n k, that is again a natural number, with n k is greater than is equals to, I can for every n belongs to natural number, so I can write it as kn. With this I am writing as kn, or I can write it as k, and then it will be n. No, this is correct. N, this is kn. Kn, this is greater than equals to n, but that is not a big deal. Kn greater than equals to n, such that mu of ekn mod is actually greater than delta for all. For if we will be able to find the delta, so that whatever n I can choose, we will be able to find an kn greater than equals to n, such that mu of kn has to be greater than delta, greater than equals to delta. So this is what it is mean by the not converging to zero. This is what it is mean by not converging to zero. Okay. Okay. This is what it is mean by not converging to zero. Now we have to give the, so that means we, if we consider fkn sequence, so that is measure of the set x belongs to, and this is already positive. There is no problem with that. That every x belongs to capital X, such that mod of fkn x minus fx, this is greater than is equals to epsilon, this is greater than equals to delta. That says, and for all n minus natural number, this is what we are getting, right? That says limit n tends to infinity, so that says fkn, but I'm just wondering one fact. Acha. Okay. As okay. Now let's consider this is as a okay. 1 minute just. Okay. So what we get here is that there is no subsequence. Sorry, there is no subsequence of this particular mkn can converge. This is the main point. As in mu of akn is always greater than equals to 0, this implies that, or one can get that here it is that, this implies that mu of, there is no subsequence, there is no subsequence of mu of there is no subsequence of mu of e kn such that limit, such that such that subsequence which converges to 0. Okay. To 0. Okay. There is no subsequence of mu kn which converges to 0. So this is the point I want to make. Okay, so that means, so that means there is no subsequence of fkn which converges in major. So this is the thing. Okay, now I'll do one more quick problem, so that after that. Okay, so let me do a quickly one other problem. So let me write the problem first. That was problem number 5. So problem number 6, what it says, that problem number 6 says, let x s mu be major space. Let fn n is equals to 1 to infinity be a sequence of real valued functions, real valued measurable functions defined on x. Let f be a real valued measurable function defined on x. Defined on x. So question is, so that the following statements are equivalent. So that the following statements are equivalent. Following are equivalent. First is that fn converges to f in major. Second is that every sequence, every subsequence of fn has a further subsequence converging to f almost everywhere, almost uniformly. If okay, this is the first problem. So this is the problem one. This is the problem one. So that basically what I have to prove, that fn converges to f in major, then this one will hold, but the other one that I have to prove, basically we have to prove that. So mainly we have to prove that, mainly we have to prove that 2 implies 1. So that means if every sequence of fn has a further subsequence converging to f almost uniformly, then fn converges to f in major. So this is what we have to prove. Okay. So let fnk be a subsequence. Okay. Now subsequence, then there exists a subsequence, further there exists a further subsequence, then there exists a further subsequence f n k l. This is where l equals to 1 to infinity, that way k equals to 1 to infinity, that way, such that f n k l goes to f almost uniformly, right? almost uniformly as L tends to infinity, right? So now, then we know that if a sequence converges almost uniformly, then it will converge in major. Okay, so then f n k l converges to f in major as a sequence if a sequence converges to as if a sequence converges as if a sequence converges almost uniformly, imply that converges in major. So let me check that I'm stating correctly. Uh, if a sequence converges almost uniformly, then if a sequence of L1 converges almost uniformly, then it is converges in major. Okay, so this is the theorem, so that's why it is converges. So that is Fn has the property Fn sequence n equals to 1 to infinity has the property that every subsequence has a further subsequence which converges in in major. Then by previous problem, that is problem number 5, Fn converges to f in major. Okay. Now also it is known that if a sequence converges in major, I think this is what we have to prove, right? So this is what we have to prove. So we are done. So that this completes the proof. Completes the proof. So what we have done? So we have every sequence has a subsequence. Every sequence has a further subsequence which converges almost uniformly. Now, if a sequence converges almost uniformly, then it is converges in major. So that means we have the property that the sequence Fn has the property that every sequence has a further subsequence which converges in major. So this will be. Now this is we can say this is part A. This is part A. Part B, sorry, this is part A, and part B is the with the same assumption that part B is that says these are two equivalent. So part B says that everything can be done by the equivalence condition if in addition mu of x is finite, measure of the set x is finite plus infinity, so that the above statements are equivalent to the following statements. Equivalent to 3. That is every sequence to the following statement. Every subsequence of Fn has a further subsequence converging to F almost everywhere. So this is also the similarly. So I will prove that we will basically prove 1 and 3 equivalent. We will prove or we can prove 2 and 3 equivalent as well. Basically, we don't need to. So let me prove 1 and 3. So we'll prove 1 equivalent to 3. So this will complete all the equivalence basically. Now clearly if a sequence converges is measured, Okay, so here is the 1 to 2. Okay, so if a sequence converges in measure, if a sequence converges in measure, then it has a subsequence which, if a sequence converges is measure, then it is known that if a sequence converges in measure, then it has a subsequence which converges almost everywhere, converges pointwise almost everywhere. The same thing, pointwise almost everywhere. And here is the needed, and mu of x is finite. Just a minute. If a sequence converges is measure. Okay, so if a sequence converges in measure, then it has subsequence which converges in pointwise another. Therefore, every subsequence f n k equals to 1 to infinity is also converges in measure, that is f n k converges to f. That implies, by the above statement, by the above statement of the theorem, of the theorem there exists a subsequence, there exists a further subsequence f nkl. This converges to f almost everywhere. So this proves one side. Conversely, if mu of x is finite and every subsequence nk has further subsequence nkl which converges to f almost everywhere, then by a theorem then by a theorem already discussed in class, that f n k l converges to f in measure for all measure as L tends to infinity. This is what we have to do. So that means every sequence, that is every sequence has further subsequence which converges to the fixed concerned, then by problem 5, the main sequence converges in major. The main problem 5, Fn converges to F in major. So this will complete the proof. So this is all. So I will stop here. This is so. Thank you.